Welcome back to ECE 320A. We'll get started with some announcements. The passport was actually due on Sunday the 20th. Hopefully you turned that in. If you have not, there's still chance for you to go ahead and submit that into the assignment Dropbox on D2L. Homeworks 1 and 2, which will occur prior to exam number 1. Homework number 1 is due in a week. That's next Tuesday. Homework number 2 is due then a couple of weeks thereafter on the 12th of February. And exam number 1 is due on February 14th. What I want to do in this lecture is actually first review our complex power expressions. We started to get there last time, but I didn't get a chance to record those, but they are in the notes. So if you want to see those at the end of last lecture, they should be at the tail end of the notes in the last lecture. I'll quickly talk through those at the beginning of this lecture. Then we will look at complex power in a network, and this network is a interconnected structure of many different loads. And what I really want to drive home is that in general you can't just add the apparent powers in each of those individual loads and assume that that's going to equal the apparent power of the combination. And we'll show that through an example via complex power in a network. And then we'll look at the power triangle and the components of the complex power, and we'll work through another example with complex power components, and then we'll start getting into working with phasors. You should already know that from chapter 9, but you need to remember that if we're adding V1 and V2 in a circuit, those are typically vector quantities, and you need to keep track of magnitude and phase, or the real part and imaginary parts of those phasor quantities. We can't just add up their magnitudes and hope that that gives us the correct answer. We have to work with these orthogonal components, the real part and the imaginary part, or the magnitude and the angle if we have it written in polar form. Let's start then with a review of our complex power formulas, and this is assuming that we have some impedance Z. Z could be some complex interconnected network of impedances, or it could just be a generic single element Z, but we're now defining the current and the voltage relative to that impedance, and I'm assuming that current and voltage are both expressed in RMS units, so the magnitude of those phasor quantities has already been converted into an RMS value, and then the appropriate angle. And really what we'll do to derive these different complex power formulas is simply to use this generalized version of Ohm's law. The voltage is equal to the impedance, where the impedance could in general be complex, have a real part and an imaginary part, times the current I. With that material, we know then we've already derived the complex power formula is the voltage times the complex conjugate of the current. That's the complex power. We may, in some instances, it may be to our advantage to only work with the current and the impedance, or the voltage and the impedance. We may not want to go ahead and find voltage and current for a particular subsystem or impedance. It may be easier to work with just current or voltages and the respective impedance. And that's what we're doing here with these different expressions. The current-based complex power expression is found by replacing the voltage by its representation in terms of impedance and current. In that sense, then, the complex power S is equal to Zi times the complex conjugate of I, and we know that a complex number times its complex conjugate is equal to the magnitude of that complex number squared. The complex power then is Z times the magnitude of the current squared. We could write that impedance Z in its rectangular form as a real part and an imaginary part, where we're now representing those as R plus JX. The magnitude of I squared is simply a number. We can distribute that number, I squared, across these two orthogonal component parts of our complex power, and now we can see that the real power, P, is just the net resistance in that impedance expression times the current squared, whereas the reactive power, Q, is X times the magnitude of the current squared. That's now, you can look at the complex power as Z, I magnitude squared, or you could now factor Z into its orthogonal components of R plus JX, and now you can see that the complex power is P plus JQ with the appropriate relationships for P and Q. And as we know, the units on complex power are volt amperes. P has units of watts, Q has units of volt amperes reactive. The voltage base, we won't go all the way to the extreme because then it gets a little bit ugly really, but the voltage based formula for complex power is similarly derived. S is equal to V times the complex conjugate of I. Now we replace I with V over Z. When we take the conjugate of V over Z, or this ratio, it's now the conjugate of the numerator divided by the conjugate of the denominator. Then in the numerator of that complex power expression, we now have V times its conjugate, which is really now the magnitude of the voltage squared divided by the complex conjugate of the impedance Z. There is now the expression for the voltage based. If we had the voltages and the voltage and the impedance, we could use this to find the complex power of that subsystem or that impedance Z. If we had the current, then we could simply use S is equal to Z times the magnitude of I quantity squared. Those are the complex power expressions. Let's now look at how we can use all of this in a more complicated network. Again, this is single phase power. We simply have one phase associated with this system, and the network could be some interconnected mess, meaning it's a collection of parallel, series, different kinds of loads that I'm labeling L sub 1, L sub 2, L sub 3, all the way up to L sub n in this network, and now we want to know what's the total complex power associated with that network. The nice thing about working with complex power is the way that these loads are interconnected, whether they're in series, whether they're in parallel, it's not important. We simply have to add up the complex powers vectorially, so we have to add up all the P's, we have to add up all the Q's, take their orthogonal combination to find the total complex power. To derive that or to represent that in an expression or in formulas, we could now, let's just establish some notation and say that the Lth subsystem, or subsystem lowercase l, let's just parameterize its complex power as being S sub L is equal to P sub L plus JQ sub L. If that's the case, then if we have a network like this, where we now have capital N identified subsystem loads in that network, how do we find the total complex power? Well, we can actually find all of the real powers for each of those individual loads and add those up. We have P sub 1 plus P sub 2 on up to plus P sub n. We can then compute the reactive parts, and we need to make sure that we're doing this algebraically. Depending on if it's inductive, it would be positive Q. If it's a capacitive reactive power, it's negative, but we keep the algebraic sum in mind when we're summing up these reactive components. So now we have Q1 plus Q2, and we keep track of the algebra. So if Q sub 2 is negative, we would really be subtracting that magnitude of reactive power from the other pieces, but we now have an algebraic combination of Q1 plus Q sub 2 on up to Q sub n. Now that we've found the total real power and the total reactive power, the total complex power, S sub capital T, and now I've remembered to put the bar above it because it is a complex quantity, we simply orthogonally combine the real power P sub T plus J Q sub T, and that's now the total complex power associated with that more involved network. Writing it out in summation form, where we now have identified each of the individual component parts, P sub L and Q sub L, we could write it also as these finite sums of P sub L and Q sub L in this orthogonal combination. Again, you need to keep track algebraically of the signs on the reactive components. In general, maybe it's not clear from what I've said, but in the next little example, I hope it becomes clear. In general, we can't just add up the apparent powers in each of these individual loads and hope to have that be equal to the apparent power of the total complex power. To see that, let's just look at a somewhat contrived example, but it's illustrative of what I want to do. Suppose we have two loads, S sub 1, or load 1 and load 2. The first load has a complex power S sub 1. The second load has a complex power S sub 2. And I could ask you what kinds of loads those are, and hopefully you would be able to tell me that load 1, since it has a positive Q, is inductive. Load 2, since it has a negative Q, is capacitive. Well, if we add those up, we can now simply add up those complex numbers, and we can add those component y. So we have 1 plus 1 for the real parts, and we have 1 minus 1 for the imaginary parts. The total complex power is now completely real. It's 2 plus J0, even though the individual subsystem complex powers had reactive pieces to them or components. So in this particular example, the apparent power is 2, or the absolute value of the complex power is just the magnitude of 2 plus J0, which is simply 2. But now I've written this in a way that it's easy, hopefully, to see the polar form of S sub 1 and S sub 2. They both are right triangles with side lengths of 1. S1 now has, for its hypotenuse or for its complex magnitude, is the square root of 2, and it's at an angle of 45 degrees. It's inductive, so that angle is positive. It has then an apparent power of the square root of 2. Likewise, S sub 2 is 1 minus J. That has unit real and unit reactive. In this case, the reactive component is capacitive, so it's a negative Q. But now we have for its magnitude still just the hypotenuse length, which is the square root of 1 squared plus 1 squared, or the square root of 2. We have an apparent power of S sub 2 of the square root of 2. If we now compare the complex power of the total, which is 2 in terms of the apparent power, I hope you can see that that's not equal to the square root of 2 plus the square root of 2. If you wanted to draw the picture, or graphically, S1 now is going up at 45 degrees with a length of square root of 2. S2, if we now connect that tail of S sub 2 to the head of S sub 1, we can now find the total power. That's just going along the red S1 plus S2 vectors, and we now end up with a completely, or a purely horizontal line, or a completely real power for the total power. And you can see now that that base of this triangle formed by the complex powers is not as long as the sum of the length of S1 plus the length of S sub 2. Meaning, I hope you can see that 2 is not equal to the square root of 2 times the square root of 2, where this is now 2 times the square root of 2, and that's now 2 times 1.4, or 2.8 roughly, and hopefully you can see that 2.8 is not the same as 2, so we can't have, in general, the apparent power equal to the sum of the apparent powers of the subsystems. Let's now look at this more explicitly with a particular example. Let's look at the complex power in a particular network. And here now I've identified 3 different subsystems. I'm calling them load 1, load 2, and load 3. Load 2 and 3 are in parallel. Load 1 is in series with that parallel combination. Assume that we now have a voltage source in RMS units of 100 at an angle of 0, so we might say that the voltage is our reference phasor. We're assuming that that now has an angle of 0 degrees. And the question might be, well, how much current is this interconnected structure of loads drawing, or what is our magnitude of I sub S bar? So we want to now find I sub S bar, and we can do that by simply adding up the component parts of load 1, load 2, and load 3. We don't have to worry that they are maybe not all in series or all in parallel. The interconnection structure does not matter, and so now we can look at our solution for finding this is to start by adding the like components, meaning add up the real components and add up the reactive components, add like components of the complex power in order to make this happen. And if you really wanted to do this quickly, you could simply start saying, well, let me just vectorially add these, meaning, well, yeah, let me go ahead and say that. So now load 1 had a real power of 100 watts and nothing vertical. Load 2 had 200 watts real. So this was now P1, this is now P2, and we had 700. I'm not going to draw this accurately, but now we had a reactive component that was 700. Then P sub 3 had a real part of 300. And a reactive part of 1500 capacitive. So now we really are, well, maybe what I should do is add these tip to tail so that we can see what we have. And then we have our reactive component, Q sub 3. And if we now started, hopefully I can somewhat draw this, the complex power is now the result of adding tip to tail all of those complex powers of the individual. So this is now our total complex power, and we can find that. You can see that we simply have to add the horizontal components with the vertical components, or the real components we add, the reactive components we add, and now the total of those will give us the total complex power. We can do that now in a more systematic way, maybe with a grid. So let's now say that we have the load, and we now have the real power of each load. We have the reactive power of each load in VARs, and we can talk about the complex power of each load, and we could even talk about the apparent power of each load. Where now for load 1, that was given as 100 and no reactive, so the complex power is 100 and the apparent power is 100. Load 2 had a real power of 200 watts and an inductive reactive power of 700 VARs, or the complex power is 200 plus J700, and if you compute the magnitude of 200 plus J700, hopefully you will obtain 727. Load number 3 was now 300 minus 1500. That was a capacitive load, or now we have 300 minus J1500 for the complex power of load 3. Again, finding the magnitude of 300 minus J1500, or the hypotenuse of that right triangle, we now have its apparent power is 1530. We could now take all of these component part totals. We add up 100, 200, and 300 to obtain 600. We algebraically combine the reactive components, and we end up with minus 800. We now combine those two orthogonal parts. We have the real part of 600, and the net reactive part is minus J800. And this, in terms of the apparent power, is now 1000, which really isn't the sum underneath those apparent powers. So let me not confuse you. Let's now look at the total apparent power, or the complex powers. The total complex power's apparent power is now the magnitude of 600 minus J800. Again, that's just a right triangle with sides lengths of 600 and 800. That's really like this 3, 4, 5 triangle, and this is now 1000 volt amperes, but that's not equal, or not the same as adding up these these apparent powers for each of the three respective loads, 1, 2, and 3. 100 is not the same as 100 plus 727 plus 1530, which that is actually 2357, where the total complex power has an apparent power of 1000, and if we added up the subsystem's apparent powers, then that's not going to be the same as the apparent power of the total complex power. Now, where were we? Hopefully you can see that if we added up those S1, S2, and S3 vectorially, we're going to now end up with the same S sub t bar, which is a distance of 600 and minus j 800. That's probably not accurately drawn, but you get the idea. What were we trying to do? If you remember, we had this complex interconnected network. We now are trying to find the current that is needed to actually produce these three sets of complex powers in the configuration that's provided, where we're now applying a voltage of 100 volts. So we're trying to find I that supplies all of that. We've now found the total complex power, that's this. We now want to relate that, but we can surely remember some of these formulas that we've been introducing in this part of the class. So we're looking for the current that supplies those, and now what do we do? Well, really what we've done is we now have reduced all of those loads down into something that really is one effective complex consumption. We now have that the total complex power of those three interconnected loads is 600 minus j 800 volt amperes. And we are given that the voltage in RMS that's powering that particular interconnected network is 100 at 0 degrees, and we want to know what current is necessary to actually achieve a complex power of 600 minus j 800. Well, we can use our very basic complex power expression now, since it's all just one. We now know the voltage, we know the complex power, the only unknown is now that current. And this formula is for these phasors of voltage and current in RMS units. That now allows us to write down the expression for this current, well, its conjugate, which we can solve for it by dividing both sides by the voltage phasor. We now have the complex power divided by the voltage phasor. This is now 600 minus j 800, all divided by 100 at 0 degrees. Now it's convenient that that voltage phasor was our reference phasor. We now just have to divide the top by 100, and we could end up with 6 minus j 8 amps RMS. Or we could have converted that rectangular form into a polar form, which is 1000, and the angle now is negative, so it's minus 53.1 degrees, divided by 100 at 0 degrees. This is now 10 at an angle of minus 53.1 degrees amps RMS. And if we broke that down into its component parts, we now have what we need, or we now know that we have 10 at an angle of minus 53.1 degrees. We could take the sine of that or the cosine of that to find the individual pieces of that, or the component parts of that current. But remember, that current was the complex conjugate. So now we have the complex conjugate of our current was 10 at an angle of minus 53.1 degrees. That's straightforward to conjugate. We just need to change the sign of the angle. And there is our current that is needed to actually supply those three interconnected loads. Our voltage V was 100 at 0 degrees. Now somebody might ask, well, what kind of load was that overall, the net load? So now we're saying, what's the type of load? And we can now go back and remember Eli the Iceman, if we need some way of remembering what the relationship is or what kind of an impedance that interconnected combination of three loads yields to the source. The source now is a voltage of 100 at a current of 10 in magnitude. Eli says V is equal to L di dt. That's the current and voltage of the inductor, and I says that I sub C is equal to C dV sub C dt. And we also know that we can use the power factor formula if we wanted to give us a clue as to the relationship of our voltage and current phasors, or the power factor really is the cosine of the impedance's angle, which is now theta sub V minus theta sub I. Or, I'm giving you a lot of different ways of thinking of this, the impedance, the net of impedance, the total impedance seen by the source, we can now use the generalized Ohm's law. That's now V over I. We know the magnitude of V, and we know the angle of voltage. We know the magnitude of the current, and we know the angle of the current, so that now we have the magnitude of Z at an angle of theta sub V minus theta sub I. So all of these are consistent. This is now theta, the angle of our impedance. So that if we looked at the power factor is now cosine of minus 53.1 degrees. The cosine is now 0.6, but we use that negative sign. Since it gets lost in the cosine operation, we now can take the cosine of that negative, but that negative now says, oh, we actually had a leading phase, and so now the current leads the voltage, or we essentially have a capacitive type load. Suppose now somebody wanted to get more information out of that system than just the overall current that's being requested. What if somebody says, how would one find the current that's supplying the third load? Let me draw the picture again. Here's a schematic of what we have. Here's S1, S2, and S sub 3. We've calculated this current, I sub S. We were given this voltage. What we now want to know is what's that particular current, I sub 3. And there's various ways of doing that, but one way would be to go ahead and say, well, this current I sub s is the same to the left of that load 1 as it is to the right. So we now know what this current is. Maybe we could use that to help us understand what we need to find I sub 3. And can we also maybe think about this voltage? That voltage is the same across both. So now if we know what this combination looks like in terms of complex power, and we can simply add those up, we now have the current supplying that load, that interconnected S2, S3 load, and the complex power formula gives us S is equal to VI star. We'll be able to back out the voltage from that piece of information. So now what I'm trying to say is let's now find the complex power associated with those two subsystems. And I'm going to call that, let's say that I call this S sub 2,3. Complex power 2,3 is now S2 plus S sub 3 in their complex form. S sub 2 was 200 plus J 700. S sub 3 was 300 minus J 1500. So that now we have 500 minus J 800 volt amperes for S sub 2,3. Now that we have that complex power and we know the current, we can use our complex power expression to find the load voltage V sub L, the voltage dropped across that parallel combination of load 2 and load 3, where we're using now the complex power S23 is the voltage times the complex conjugate of the current. Solving that for the voltage, V sub L, is now S23 over the conjugate of I sub S. This is now 500 minus J 800, all divided by 10 at an angle of minus 53.1 degrees. We can find the polar form or magnitude and angle of that rectangular complex power by finding the magnitude. That's just the hypotenuse of that right triangle, and the angle is going to be the angle associated with 800 in vertical and 500 in horizontal, or we now have 943 at an angle of minus 58 degrees, all divided by 10 at an angle of minus 53.1 degrees. Divide the magnitudes, algebraically combine the angles or subtract the denominator angle from the numerator angle, and we now end up with our voltage dropped across loads S1 and S2 that are in parallel is now 94.3 at an angle of minus 5 degrees. Now that we know that voltage and we know the complex power of S3, we can now find I sub 3, again using the complex power expression. Or complex power of load 3 is the voltage dropped across that load times the current going through that load, which we don't know, but we're going to find. That's the conjugate of I sub 3. Solving for that, we can see then that the complex conjugate of I sub 3 is S sub 3 divided by V sub L. That's now 300 minus J 1500 all over 94.3 at an angle of minus 5 degrees. Again, since we are performing a division, we probably want these complex quantities in polar form. The polar form of the complex power of S sub 3 is 1529.71 at an angle of minus 78.69 degrees, all divided by 94.3 at an angle of minus 5 degrees. Or that now ends up being 16.22 at an angle of minus 73.69 degrees. Finding the conjugate of that, which will give us the actual current I sub 3, we simply change the sign of that angle so that now I sub 3 is 16.22 at an angle of 73.69 degrees. And again, that's in RMS units. So you can see that these complex power expressions are very useful to helping us back out individual parts of answers, and it was also nice to find the total complex power by simply adding up all of those component parts of the individual loads. Let's now return to this power triangle and really just sort of remind ourselves of the relationship between all of the parts or sides of this right triangle that forms our power triangle. So now we're relating different power components. Where our picture has P, it has Q, and it has the complex power S, which is the hypotenuse of that right triangle, where the right triangle has a real side length of P, a vertical side length or reactive side length of Q, and this angle theta is really the angle between the voltage and the current. Just drawing that complex power triangle helps us, reminds us of what we're dealing with expression-wise. So that now we have S is equal to P plus JQ, and we also know that the power factor is the cosine of theta. And looking at that triangle, we can see that P, the real part, is really just the projection of that complex power onto the horizontal side of that right triangle, or that's now the hypotenuse, the apparent power, times the cosine of theta. Or it's simply the hypotenuse times the power factor. Or if somebody wanted, they could say, oh, I actually need the power factor, and the power factor now we can find if somebody gives us the real power and the apparent power, or we can know that the apparent power is just the magnitude of V times the magnitude of I for that particular system. Likewise, Q is the vertical component, the reactive piece, which is now simply the magnitude of the complex power, or the apparent power, or the hypotenuse, times the sine of theta, and we've called that sine of theta the reactive factor. We can also relate or find that angle if we wanted to, if somebody gave us Q and P, where now the angle theta is just the inverse tangent, or the angle that has a tangent of Q over P. Likewise, one more piece of information is if that angle theta is positive, Q is positive, or that corresponds to a load that looks more inductive, or a load that has a current that's lagging the voltage. And we can see that if we just write down Eli and see that the current is following or lagging the voltage. If we have a negative angle theta, then we have just the other type of reactive load, which is capacitive. Or leading. And so now we have ice, if we wanted to look at that. Let's now use these formulas to actually help us analyze another complex power network. For this example, let's say that one load is now 100 kVA with a power factor of 0.8, and let's say that it's lagging. So that now we're given, or we're now talking about different loads being described or identified maybe with different components than maybe what we're used to seeing. We maybe up to this point always thought, well, you give me a real part and a reactive part and I'll be able to work. Well, now maybe we'll give you another piece or pieces of that complex power triangle. Let's say that load 2 is now 50 kilowatts with a power factor of 0.9, and it's leading. Hopefully now you're starting to see that the units that people now use give us information about what these loads look like or what they consist of. Suppose now that somebody tells us that the voltage applied across these two parallel loads in this case is 200 volts, and it's our reference phasor, so it's at 0 degrees, and we'll assume this is now in RMS units. We don't, or we haven't yet been given, or don't know, the current necessary to supply those particular loads. And the strategy that we had before we can use again. We found in the previous example, we simply found the total complex power, and then from that we're able to back out from our complex power expression this current I sub S. Let's try that again, except now we're not given these load powers in terms of these orthogonal components. We're given in mixed different quantities. So the strategy now is first to try to find the total complex power, of those two loads in combination, and then once we have that, the voltage is the same across both. We can then use the complex power formula or expression to find the current supplying the loads. And that current is now I sub S bar. Let's do that now for these different pieces. We have load 1 and load 2, and again, they're not all giving us the same flavors of powers. We have different powers, and we determine what powers we have by the information that's been given to us. And here, the key piece of information concerns or is connected to the units. For load number 1, what can we back out of that? Well, now I think sometimes it's helpful to just draw the complex power triangle and see what we have that we're working with. We were told that we had for load 1 100 kVA. Well, VA is the apparent power, that's the magnitude of our complex power. And that complex power has a reactive component and it has a real component, and I actually drew this hypotenuse going up relative to the horizontal axis, and that's because we were told that the angle was lagging, or lagging means we have an inductive load. That means we have a positive Q. That's why I was able to draw this angle in the positive direction. Positive with respect to the horizontal real axis. Here's the real axis, and these angles are all measured relative to the horizontal real line, and in this case in a counterclockwise direction. So if we're going counterclockwise relative to the real line, now we're moving through a positive angle. With this particular picture, we were given the hypotenuse, or the apparent power, of load 1, which was 100 kVA. That was the apparent power. Theta 1 we were sort of given in the form of a power factor. We were told what the power factor was, but the power factor is just the cosine of theta, so we can invert that expression. We can take the inverse cosine of both sides to find theta. We now have the inverse cosine of 0.8, and we can use the fact that it was lagging to give us our sine of positive. And now we know that theta 1 is 36.9 degrees, where Eli tells us the positive nature, or theta 1, is now theta v minus theta I, and we know that theta v minus theta I is 36.9 degrees. P1 is now the apparent power of load 1 times the cosine of theta 1. 100K times 0.8, again cosine of theta 1 is the power factor. This is now 80 units of watts, 80 kilowatts. Q1 better be positive since our angle is positive. And the sine of 36.9 degrees is 0.6. Or now we have 60 kilovars for our reactive component of load 1. Now we're in business in terms of adding these orthogonal component parts. Q1 and P1 we can now add if we have those same kinds of components for load 2. Let's compute those now. For load number 2, we were given the following information. We were actually given P2, the horizontal length. We were told that it was leading, so now we know that we're going down relative to P2. And we want to now, maybe we don't need that complex power in a vector expression, but we do need Q sub 2, and we were also told the power factor of load 2, so indirectly we have theta sub 2. In this case, we were given the real power of 50 kilowatts, and we were told indirectly what theta sub 2 was by the power factor. Again, the power factor is the cosine of that angle, and we were told that it was leading, so we know this angle is negative, and we take the inverse cosine of the power factor, which was 0.9, or we now know that we have an angle of minus 25.8 degrees. P2 we knew, but we can use that to find the apparent power, since we have P2 as the apparent power, or the magnitude of the complex power for load 2 times the cosine of theta 2. We know the cosine of theta 2 is 0.9, so we can use this expression to actually back out the hypotenuse, or the apparent power associated with load 2 is now P2 divided by the cosine of theta sub 2. In this example then, the apparent power for load 2 is 50K divided by 0.9, or we now have 55.6 kVA. Q sub 2 is now that apparent power times the sine of theta sub 2, or that's now 55.6 K times the sine of minus 25.8, and now that minus sign doesn't fall away because it's going through the sine expression, and this Q sub 2 is now minus 24.2 kilivars. Now we have all of the pieces that we need in the appropriate directions. We have all of the real components, we have all of the reactive components of loads 1 and load 2. Now we can compute the total complex load power, and that's going to be now the complex power total is the algebraic sum of complex power 1 plus complex power 2, or that's 80K plus J60K plus 50K minus J24.2K, or that's now 130K plus J 35.8K, and that's volt amperes. That's our total power. We can now use that to find or back out our current that's now needed to sustain those two loads. This is now part B. Using our complex power formula, S sub T is the voltage, that was the same across both loads, times the conjugate of our current. We can solve for that conjugate of the current. That's now S sub T divided by V. This, since we're taking the ratio, we might as well find the polar form of that rectangular complex power. This now is going to be 134.8 K at a positive angle of 15.4 degrees, since Q was positive in the total complex power, all divided by 200 at 0 degrees. that now says that I sub s star is, remember this was now 134,800. That was now 134.8 K. We divide that by 200 and we end up with a large current of 674 at an angle of 15.4. But if we go ahead and just say let's find the actual current, we can negate that sign so that the current is going to be at minus 15.4 degrees. And now we can say, okay, what happens to our load current relative to the voltage? Well, the voltage, remember, was at 0 degrees, and this we just found was minus 15.4 degrees. And so now we have voltage here and current here. And if we wanted to think about this, we're now sitting over here and watching these phasors rotating in a counterclockwise direction. This theta sub I current relative to theta sub V is behind. So theta of this interconnected load, this is now the net of these two loads. Theta is now theta sub V minus theta sub I. And now we see that the current actually lags the voltage in this particular system. And because of that, now we have an impedance, net impedance, that looks more inductive. So now what we want to do is pick up from that point. We'll talk about voltages and currents. Now these are phasors, and it's important to keep track of not only the magnitudes but also their angles relative to each other, or breaking these voltages and currents down into their real parts and imaginary parts. We'll pick up at that point next time.